In model 21, we will continue with our study of RSM. We will go ahead and take up the concepts like first order design, then second order design, then first degree, second degree, and then the concepts of orthogonality. We will be a bit technical in our description of the model, and then slowly the terms and concepts will come up. So let's see what we have in this module. Again, it will be mostly in the form of MCQ. Okay, Sagorika, let us get started. Let me read out question number 1. In a 2 cross 3 factorial experiment involving the factors a and b, first option, there is scope for estimation of linear effect of A and quadratic effect of B. Second option, there is scope for estimation of quadratic effects of both A and B. Third option, there is scope for estimation of interaction between A and B only in a replicated experiment. The fourth option, there is no error degree of freedom even if the interaction effects are assumed negligible in a single replication. So let's try to understand. When it says 2 cross 3 factorial experiment involving the factors A and B, that means A is at 2 levels and B is at 3 levels. Therefore, the levels of A are generally written as 0 and 1, and the levels of B are written as 0, 1 and 2. So it only shows that A has a linear effect, even if A may have higher order effect, but we are not in a position to find it, and B, at most we can go for a quadratic effect. For B it will be linear and quadratic, and for A it will be linear. If we are talking about crossing them, it will linear cross linear, linear cross quadratic, that's it. That is what is happening here. So we write main effect of A, then main effect of B, then the quadratic effect of B, B square, and then A into B and A into B square. These are the 5 components, A, B, AB, B square, AB square. Okay. Out of 2 into 3, that means 6. There are 5 effects and interactions, and these are the 5 which one can spell out. Okay. So there is scope for estimation of linear effect of A and quadratic effect of B, yes. There is scope for estimation of quadratic effects of both A and B, no. There is scope for estimating the interaction between A and B only in a replicated experiment, not necessary. Here also we can get for A cross B and A cross B square. Okay. There is no error degree of freedom even if the interaction effects are assumed negligible in a single replication. No. If I assume that the interactions are negligible, they can count for error degree of freedom. Okay. So the most plausible answer here is answer number A. Please read out.
Okay, sir. So in a 3 cross 3 factorial experiment involving the factors A and B, the options are there is scope for estimation of linear and quadratic effects of A and B. The second option is there are 2 degrees of freedom for error without any assumption in a single replication. The third one is there are 5 degrees of freedom for error under certain assumptions on the interaction effects. And the fourth one is there is no error degrees of freedom even if the interaction effects are assumed negligible in a single replication.
Okay, let's see. This is an example of a factorial experiment with both the factors at higher levels. So it is 3 cross 3, we write it as 3 square.
Yes.
2 factors each at 3 levels. Altogether there are 9 level combinations, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2.
Okay.
And in terms of Yates notion, 1 goes there and then A square, B, B square, AB, AB square, A square, B, A square, B square.
Okay.
These are the 9 combinations that are coming up. Okay. You have altogether 8 effects and interactions apart from the mu. Okay. So that is where we stand. Now, for a single replication, there is scope for estimation of linear and quadratic effects of A and B. The answer is yes. There are 2 degrees of freedom for error without any assumption in a single replication. Unless you make any assumption, you cannot just get error degree of freedom because everybody is accounting for either an effect or an interaction. There are 5 depth for error under certain assumptions on the interaction. That's a vague statement. You can always assume something negligible and then you can count on them towards error.
Okay.
That's not a well formulated answer.
Okay.
There is no error degree of freedom even if the interaction effects are assumed negligible. That's not true. If we assume the interactions to be negligible, you can push them to the error. Therefore, the most plausible answer is again A.
So, in a 2x3 factorial experiment involving the factors A and B, there is scope, the options are pretty similar. There is scope for estimation of linear effect of A and quadratic effect of B only in a replicated experiment. The second one is there is scope for estimation of quadratic effects of both A and B. The third one is there is scope for estimating interaction between A and B only in a replicated experiment. And the final one is there are error degrees of freedom if the interaction effects are assumed negligible in a single replication.
Okay, the first factor is at 2 levels, second factor is at 3 levels.
Yes.
We can think in terms of the linear effect of A and both linear and quadratic effects of B.
Okay.
Given this understanding, answer A talks about there is scope for estimation of linear effect of A and quadratic effect only in a replicated experiment. That is wrong. It does not have to be replicated.
Okay.
There is scope for estimation of quadratic effects of both A and B. That is decidedly wrong. There is scope for estimating interaction between A and B only in a replicated experiment. That is also wrong. The right answer is there are error degrees of freedom if the interactions are assumed to be negligible even in a single replication. Okay? So the correct answer is D.
Okay. So here is the next one. In a 2x3 factorial experiment involving the factors A and B, the ANOVA table does not provide any error degrees of freedom. The ANOVA table indicates 4 degrees of freedom for error under certain assumptions, or the ANOVA table provides error degrees of freedom under a replicated experiment, or it might be there is no error degrees of freedom even if the interaction effects are assumed negligible in a single replication.
Naturally, D is wrong because if you assume the interactions to be negligible, you can push them to error. That is not true. Also, under a replicated experiment, the ANOVA table can always provide error degree of freedom. That is the most plausible answer, C. Okay, let's see. So here, as I said, I am going to give the composition of the blocks. The moment I say I am giving composition of a block, I mean it is a blocked experiment. That means there has been some confounding and I am giving the formation of the key block.
Okay.
Then you have to decide this key block means what effects have been confounded and so on. It's very interesting. Let me read the first one. You have a 2 square factorial experiment involving the factors A and B. Then what is the interpretation of the level combination AB plus A minus B minus 1 divided by 2? That factor half can be withdrawn at this moment. We just talk about the numerator. AB plus A minus B minus 1, what does it represent? Does it represent the main effect of A or main effect of B or the interaction between A and B or the error contrast? We have to remember what are the representations of the effects and interactions. Main effect of A is represented by A minus 1, B plus 1. For B, it is A plus 1, B minus 1. For AB, it is A minus 1, B minus 1. It's a pretty simple question. You write each of them and then find out the linear combination of all the 4 and you try to match the one that is coming up here. That is one way of doing. Other way is just look at this quantity. AB plus A minus B minus 1, do a factorization, take A common B plus 1, minus 1 common B plus 1, A minus 1 B plus 1. That refers to main effect of A. Straight away. So there are so many ways of verifying this thing. Interesting. Pretty simple, but basically coming
These
from the concept.
Yes. So in a 2 square factorial experiment involving the factors A and B in the usual notations, the same thing, the AB minus A minus B plus 1, all thing divided by 2 represents,
etc. etc.
something.
So this time you will get A minus 1 into B minus 1. So that would mean interaction effect between A and B. Okay?
In a 2 square factorial experiment involving the factors A and B in the usual notations.
So this is referring to A plus 1, B minus 1.
Yes.
So it is main effect of B.
Yes. In a 2 cube factorial experiments involving the factors, here an additional factor is there, A, B and C. In the usual notations, C minus 1 into this,
etc. That represents
that
what?
represents
The
what?
moment you see C minus 1, you know that the factor C is already involved. So you have to only look for the other 2. And AB minus A plus B minus 1, that is A plus 1, B minus 1. Therefore, A plus 1, B minus 1, C minus 1. It is referring to the interaction between B and C.
Yes.
Okay?
So here, the three factors are there. It's a 2 cube factorial experiment, and this thing, that is C plus 1 into AB minus A plus B minus 1, etc.
The moment you see C plus 1, C has never read out. You don't have to worry about C. Now if you look inside, A goes common, A plus 1, B minus 1. It is the main effect of B. That's it.
So here also, it's 2 cube factorial experiment, so 3 factors are there. And the thing is A minus 1 into B minus 1 plus BC minus C, whole thing given by 4.
So you take C common, B minus 1, C plus 1, B minus 1. So A minus 1, B minus 1, C plus 1, interaction effect of A and B.
A and B, yes. So here, in a 2 to the power 5 factorial experiment, a single replication carries 5 into 2 minus 1 is equal to 9 degrees of freedom.
Totally wrong, because 2 to the power 5 means 32.
Yes.
Minus 1, 31.
Should be
It's the wrong interpretation. Okay.
Yes.
Next,
it's ANOVA table for main effects and 2-factor interactions altogether absorbs 20 degrees of freedom.
there are 5 factors, there are 5 main effects, and 5 combination 2 is 10. There are 10 2-factor interactions, therefore 10 plus 5 equal to 15. Altogether 15 main effects and interactions together. So that number 20 is not correct.
So the third one is ANOVA table can indicate error degrees of freedom under certain assumptions.
Yeah, we can assume the higher order interactions to be negligible, and you can take them together towards formation of the error. Yes.
This looks pretty similar with those we had discussed earlier. Here it is also a 2 cube factorial.
It's a straightforward problem.
Yes,
Next,
we can do.
Yeah.
In a confounded 2 cube
good.
factorial experiment with 2 blocks and interaction ABC confounded. In the usual notations, the key block is represented by which of the following?
Very good problem. Okay. The moment they say it is a confounded 2 cube factorial experiment with 2 blocks and interaction ABC confounded, immediately you know how the confounding has been done, because you are looking to A minus 1, B minus 1, C minus 1, and you are expanding it, and then you are getting 4 in one direction, 4 in another direction, and those are the 2 blocks used in the confounding process, in the process of formation of the confounded experiment. Okay, so these are the 2 blocks that have been formed, and the definition of key block is the one which includes 1. 1 means all at 0 level, 0, 0, 0. So we know A minus 1, B minus 1, C minus 1, we expand, we try to identify the block with 1, and we match with the solution that is given here. Okay, that's pretty simple.
Yes.
If you have the concept, then you can immediately verify.
Yes. Here it is a 2 to the power 5 factorial experiment.
2 to the power 4.
4, sorry. Factorial experiment with 2 blocks and interaction ABCD is confounded.
Very good.
So with the
so it amounts to A minus 1, B minus 1, C minus 1, D minus 1.
Yes.
You write it down, you get 4 and 4. The 4 with 1, the key block, 1 you have to identify and you have to match. You don't have to know everything. The moment you start writing, you are matching 4. So they are not showing all 8. They are showing just 4. You know, they're good enough for you to identify.
Yes. In a confounded 2 to the power 4 factorial experiment with 4 blocks and interactions AB, CD and ABCD are confounded.
Right.
In the, so what would be the
key block?
The key block.
So interesting problem. So because there are 4 blocks, 3 degrees of freedom will be gone due to blocks. Therefore, they will confound 3 effects and interactions. But only 2 of them can be independently selected. Other one is their generalized interaction. That is exactly what is happening here. You are confounding AB, you are confounding CD, and as a byproduct, you are confounding ABCD. For AB, you know A minus 1, B minus 1. For CD, you know C minus 1, D minus 1. When I say A minus 1, B minus 1, in a 2 to the power 4 factorial context, I mean A minus 1, B minus 1, C plus 1, D plus 1. When I say CD, I mean A plus 1, B plus 1, C minus 1, D minus 1. So you write out AB, you write out CD, you get 8, 8, 8, 8, you take their intersection. They will give you 4, 4, 4, 4 in 2 by 2 cell. One is corresponding to AB, other is corresponding to CD. You get 4, 4, 4, 4. From there you bring out the one having the key block formation with 1, and those are the 4 that you are talking about.
Okay.
And the key block is represented by etc.
Okay.
Good problem. Next.
So that's it.
Is that all? Okay, can you go back please?
Yes.
Let me repeat again. So how do I form a 4 block 2 to the power 4 factorial experiment confounding the interactions A, B, C, D and A, B, C, D? Let me explain again. For A, B, I look at A minus 1, B minus 1, C plus 1, D plus 1. I split into 8 and 8.
Okay.
For CD, I look at A plus 1, B plus 1, C minus 1, D minus 1. I split again all the 16 into 8 and 8. Now I will find that if I cross classify these two, then there will be 4 cells with A 4, 4, 4, 4. They correspond to AB with a plus sign, AB with a minus sign, CD with a plus sign, CD with a minus sign.
Okay.
And then we will be finding the key block will be common to both of them, and there will be 4 treatment combinations common to both.
Okay.
And those are the 4 that one has to identify. Okay? Good enough. So in model 21, in a sense, we have described different types of models, understanding the model which is described, and then taking up an appropriate formula for the model expectation, counting out the nature of the parameters involved and the number of the parameters involved, and thereby looking into a framework for collection of data points and talking more about the number of distinct data points that have to be collected so that one is in a position to estimate all the model parameters unbiasedly. It is more or less an exercise in linear models subject to our understanding of the nature of the response surface. And we talked about the number of regressors starting from 2, 3, 4 onwards, etc. Depending on the number of regressors, the number of design points goes up, and then we have to suitably think about the choice of the design parameter, the choice of the points in the experimental setup, so that the response surface methodology can be suitably adopted and we can have an unbiased estimate of all the model parameters. That is mostly what we took up. So in the next module, the last module, we will talk more about rotatability. We will come back to the rotatability concept and try to understand more of it. Yes, Sagorika, let us take up some questions again in that format. There are some theoretical questions followed by MCQs.
Okay.
Let me read question number 1. You have a 2 cross 3 factorial experiment and it is laid out in 2 replications. You are supposed to prepare the ANOVA table and show the algebraic expressions for all relevant sum of squares in the table. Because it is 2 replications, you will have replication degree of freedom 1, that is the standard computation of the sum of squares. First replication total square divided by 6 plus second replication total square divided by 6 minus CF, the correction factor, okay, which is nothing but the grand total whole square divided by 12. That's it. And then you are talking about the main effect of A, and then for B, because it is at 3 levels, you are talking about B and B square, and then AB square. These are the 5 components. For each of them you write down the sum of squares expression, and then you combine from the 2 replications, and thereby at the end you get the error degree of freedom. This is a very pretty standard question. There is nothing challenging over there. Let me read out the question number 2. Now we have a 3 cross 4 factorial experiment, again laid out in 2 blocks of size 6 each. 3 cross 4 means there are 12 level combinations, and you are thinking in terms of 2 blocks of size 6. So 6 plus 6, that makes it 12. You suggest a block composition. The moment you say there are 2 blocks, you are thinking of confounding. So you have to suggest a block composition which will ensure estimability of all main effects of the 2 factors, carrying respectively 2 degrees of freedom for the factor A at 3 levels and 3 degrees of freedom for the factor B at 4 levels. You have to maintain estimability of the main effects of both A and B, and then you have to suggest a block composition. Naturally, you have to think of higher order interaction going out. Okay. Question number 3, you have a 2 to the power 4 factorial experiment laid out in 2 blocks and you are given the key block. Examine the deficiency of the design. So what is the deficiency of the design? So mainly when you give me a key block, I know the complementary part, I know the other block. So these are the 2 blocks comprising the full 2 to the power 4 factorial experiment. Now I know the expressions for all main effects and interactions. I know when the main effects and interactions, their algebraic expressions are orthogonal to the 2 block compositions. They have to be orthogonal to the 2 block compositions so that the block degree of freedom does not eat up any of them. So I have to make sure what is my expression for A minus 1, B plus 1, C plus 1, D plus 1. I write it down. I find out 8 and 8. And for I know the composition of the 2 blocks. I have to see whether the block contrast is orthogonal to the contrast formed for A, etc., etc. So that is how I have to make sure at least all the main effects and interactions are saved or not. And that in the process I will examine what is the deficiency of the design. If it is already confounds one of the main effects, then there is a problem. That is the kind of thing we are talking about. The last one is, you have a 2 to the power 5 factorial experiment laid out in 4 blocks. You know that there are 3 degrees of freedom due to blocks, and you are given the key block having 8 compositions. Examine which effects and interactions have 100% loss of information. So there are effects and interactions which have been totally gone because of this blocking. So you have to identify them. Okay, that is the type of question coming up here.
So here are some
MCQs.
Please read it. In a 3x4 asymmetrical factorial experiment laid out in 2 complete replications, all effects and interactions can be estimated and tested without any assumptions whatsoever. So this is the statement, and we need to say whether this is always true, whether this is not necessarily true, and if it is, it can never be true.
Is it a replicated experiment? Or they are complete replications? Yes, there are complete replications, no blocking, nothing. Replication 1, all the 12, replication 2, all the 12. So you have enough degree of freedom for error. We don't have to assume anything, all the effects and interactions can be estimated, and we have, because of replicated experiment, we have enough degree of freedom for error. Therefore, we can always go for estimation and testing of all the effects and interactions without any assumption whatsoever. So, answer is A. What is the next one?
Sir, in a 3x4 asymmetrical factorial experiment laid out in two blocks of equal size, main effects can always be estimated. This is the statement, and the same options are there. This is always true. This is not necessarily true, and it can never be true.
Okay, let's see. The moment you say 3x4, there are 12 level combinations, and you are it is laid out in 2 blocks of equal size 6 and 6. The moment you say 2 blocks, there is a blocking coming up. Due to blocks, there is 1 degree of freedom. So it must be taking account of one of the effects and interactions in the whole process, and it all depends on how the 2 blocks have been formed. You know, formation of the 2 blocks naturally. What I have done, underlying blocking mechanism, maybe I have, in the process I was not careful enough, I have confounded one of the main effects. It is possible. Therefore, the main effects can always be estimated. I cannot say that. It depends on what has been confounded, what has been taken up as the defining set in the process of going for this blocking. Okay, it all depends on how you have done the blocking. So it is always true, that's not true, not necessarily true, that is the thing.
So here are 2 more questions. The key block in a 2x3 asymmetrical factorial design laid out in 2 blocks is given by this in usual notations. So the question is, this design confounds main effects of A. These are 4 options.
Okay. So 2x3 means 6. If it is laid down in 2 blocks, 3 and 3. So you can see 1 B square and the rest is with A B square. That is the composition. So the moment you see this thing, this one has got level 0 of A and the other one has got level 1 of A. Therefore block 2 minus block 1 straight away is talking about the main effect of A. Therefore the main effect of A has been confounded. Next one.
the key block in a 3x4 asymmetrical factorial design laid out in 2 blocks is given by
etc. etc.
this thing.
Then the
usual
design
notations.
conforms, etc.
Yes.
Okay. So you have to figure out these are the 6 here, and then we have the remaining 6 on the other side. You know the contrast that is formed out of the 2 blocks. Then you have to see if any of the effects and interactions have been confounded or not. That's the whole idea.
Okay.
Okay.